Alright, y'all. Welcome to 12.1 Part B. Today we're going to look at our estimating these parameters. And we're going to do that by creating confidence intervals by which we think the slope could be of a certain line, or we're going to test the slope to see if it could be the actual population slope if we're accurate. Alright. So remember, this is our population line. This is going to be an estimate. This is what we're used to doing. Like, this is a hypothesized y based on an x given our slope. Okay? So when we do this, what we're doing is we're taking our y-intercept of our estimate is giving us a guess for what the population y-intercept is. And remember, y-intercept is interpreted as if x is 0, that's our value. Our slope of our statistic estimates the population slope, and our standard deviation of our sample estimates the population standard deviation. Okay. Tip on your calculator: they don't use this notation. It's just going to be y hat equals a plus bx. Keep that in mind when you're using your calculator to do problems. Thank you and good day. Alright guys, so when conditions are met, the sampling distribution of the slope B is approximately normal, where your population mean equals your estimated mean. And we do our standard deviation this way. We talked about that last video. And if we want to call it in to do standard error now, that's standard deviation. For standard error, we do n minus 1. Okay? Do n minus 1 for standard error. Keep that in the back of your noggin. We'll go over that more someday. So the standard error is how far a sample slope typically is from the population, the true slope. Standard error is how far our sample usually varies about the true slope. Alright, so we're dropping those helicopters again, right? Pause this and read it, and we're going to go through each question. Read it, learn it, love it. So they're dropping 70 paper helicopters. They're looking if height and flight time are correlated and if you can estimate one off the other. So we have our constant coefficient T and P. Our drop height coefficient, remember that's your actual slope right here. Our standard error coefficient, our T, which is not the T you're thinking of, and our P. We're going to talk about that later. So what's the estimate for my y-intercept according to this data right here? Well, it would be our constant we got 20.03 7 . I had to go fix that. That's not 20. This should be a negative right here. That's an eraser. What in the world is going on? Alright, that's negative 0.03761. So if you drop it from 0 centimeters, it'll take, our prediction is negative 0.03761 seconds to land on average. I don't know why this won't land. There it is. So that's negative 2, not 2. Okay? Negative, not 2. So what's our estimate for our slope of the population? Well, we go to our chart. There's our slope right there. It's the coefficient of the drop height. So it's 0.005724 for each increase of 1 centimeter. The flight increases by 0.005724 seconds. Okay. By the way, this here gave us a y-intercept. I don't know what's going on there. And what's the estimate for our standard deviation? Well, our estimate for our standard deviation is our standard deviation of the sample. Ta-da! So the actual typical flight typically varies by 0.1681881 from the time predicted by the least square regression line using drop height. Now for standard error. Oh snap, it's given to us as well. Our standard error is actually right here. We don't have to calculate it. It's done. So what this is saying, how far our samples will be away from the true. So if we did this a bunch of times, the sample regression would vary by about 0.000218 of the true regression line for predicted flight time from the drop height. Now, how do we find a confidence interval for our slope? Well, we're going to take a statistic plus or minus critical value times the standard deviation statistic. Point estimate plus or minus mou, right? So for this one, what we're actually doing is we're taking our sample slope, and we're adding and subtracting t times our standard error of our sample. Okay. Now for this one, to find t, our degrees of freedom are n minus 2, not n minus 1, n minus 2. All right, n minus 2, not 1, 2. Okay. Now your calculator will not give you your t value. Don't use your don't use the readout. That's not the right t. Problem. Read it. Let's see what the question is later. So pause it, read it, love it, learn it. We have miles driven compared to price. The theory is the more miles, the less price. So here's a bunch of plots. We want to make a 90% confidence interval for the slope of this population. Okay? We're going to state plan do this beast. Alright, look at this. Pause it if you need to. So first we're going to state. So what are we finding? A 90% confidence interval for the slope of the population regression line for price to miles driven of a super crew. Okay? Plan. We got to do linear every time. Is it linear? Yes. Not a U over here. Is it independent? I think 16 is less than 10% of all the super crews. Is it normal? Yes, I would say there's no outliers or skew. Equal standard deviations. I gotta go back again. Yes, those are randomly scattered. There aren't more far apart in one spot than the other. Random sample? Yeah, it was. Yes, it was. So we planned it. We're doing a t interval for slope. Time to do it. Degrees of freedom. We're going to do 16 minus 2 and get 14. From that information, we get t to be 1.761 using our table B, I do believe. If you need help on that, make sure you let me know. So we take our slope. So we're doing our computer readout now. We're going to take our slope, which is the coefficient of miles driven. Then we're going to plus minus our t times our standard error. So slope B1, standard error. I know I'm going quick, guys. So we do our slope, our coefficient of miles driven, plus or minus our 1.761 from the table, times our standard error, which is 0.0306996. So we get this answer right here. All right. So, what's that mean? That means we are 90% confident that the interval from that to that captures the true slope of the population regression line for price to miles driven for a F-150 Super Crew listed for sale on Autotrader.com. The computer readout's usually going to be given to you guys, so you just got to plug it in and chug it. Find your t-value. All right. So here's how you do a linear regression t interval. So what you do is you'd plug in the miles driven and your price in L1 and L2, and it will give you the same answer. Okay? Linear regression t interval. You have to plug in your statistics, though. Oh, yeah, usually don't have plugins in your calculator. Make sure you guys read it and see what's actually going on. Most of the time they give you the numbers, and then you have to figure out what those numbers mean. Okay? Very infrequently do you have to do this out longhand. I've never seen it. Alright, now how do we find our p-values in performance significant tests? Well, remember your test statistic is always your stat minus parameter over standard deviation. It's like your z-score, right? We're going to be using t, so it'll be like your t-score. Alright? You can read that. Just remember your hypothesized slope is going to be 0. Okay? It's going to be 0. Assuming there is no slope, nothing between them, no regression. T is still n minus 2 as well for your degrees of freedom for these ones. We're not going to do a whole lot with that stuff. You can pause this and read it, learn it, love it. Crying babies. Just crying make you smarter. If that's true, my daughters are geniuses. And I am too. But read it. We got the table there. Pause if you need to. There's all the stuff we need right there. See, usually they'll give you this stuff. All right. So, state plan do time. I'm going to check for liner right now while I'm on. Well, I think actually, yeah, they do. State. Our null hypothesis is that the slope is 0. We're going to assume 0 slope. And we think it's greater than 0. We think it's a positive slope. Okay? We think it's bigger than 0. So that is the slope of the regression line to IQ compared to peak number of crying for a baby. We're going to use alpha as 0.05. Plan time. Is it linear? Yes, there's no defiant U in the residual line. Is it independent? Yes, 38 is less than 10% of all the babushkas out there. Guarantee it. Is it normal? Yeah, very normal. That's a very normal curve right there. Equal standard deviation? I would say so. It's not wild. Has to be wild. Random sample of 38 infants. We can run this test, guys. Oh, do. No calculations required. Our t-value is 3.07 if you're looking at the chart, because our degrees of freedom was 36. Right? And we're doing 95% confidence. But what's important here is our p-value is on the table. It's on the table, the changing table, some would say. P-value is on the table. We do have to divide it by 2 because that p-value is for 2 tails. So when they do their p, they're doing 2 tails. But ours was only greater than. So we divide it by 2 because it's 0.004 on both sides. So that means each side is 0.002. Alright, so divide your p by 2 if you're doing a 1-tail test. 2-tail test, leave it as it is in the chart. So, can we make a conclusion? Yeah, we can. That's less than 0.05. So we can say there is evidence that there's a positive relationship between number of crying and IQ score in infants. And I've read this study before. It's pretty interesting. All right. So we reject the null that there is no difference, and we say, or there is no linear relationship, and we say there is convincing that there's a positive linear, because that's what we were testing. Okay, we were testing whether or not there is a positive linear condition. Now, if we did a two-tail, we'd say there is some sort of linear. All right. You can also do this in your calculator. They're going to give you the readout. That's how you do it. LinReg t-test. Plug in your data in L1 and L2. It'll give you the same information, T and P in degrees of freedom. Okay, that's it. Have a great day, y'all. Uh-oh, how do I stop? I hope I was recording.